Now let's take a look at example number 2. Suppose that f of x, y, z is a function of 3 variables, and let's pretend that it has continuous second-order partial derivatives. Okay, so if that's the case, can I go ahead and attempt to find a formula for the curl of the gradient of f? Okay, so this is kind of an interesting problem here in that we're going to be interested in starting with a function, taking its gradient, and then establishing a curl. Okay, so let's start with just attempting to find the gradient. Well, since the function really isn't specified in terms of like I have a formula for it, the best we can do when trying to establish the gradient is to at least kind of establish what its general structure looks like. We know that the gradient is going to be the partial of f with respect to x, partial of f with respect to y, and a partial of f with respect to z. And again, since I don't have a formula for f, that's about the best I can do. However, that does allow me actually to go ahead and start to compute the curl of f, or sorry, the curl of the gradient of f, because I can go ahead and start to set up again that cross product calculation. So again, I know I'm going to have partial with respect to x, partial with respect to y, partial with respect to z, and then I'm going to have my gradient going along here on the bottom. I have my I, my j, and my k, and I'm ready to calculate. So let's see. This is going to turn into something like the following. I'm going to have to do, starting here, with a partial with respect to y of this partial of f with respect to z. Notice what that means is that if I've already taken a partial of f with respect to z here, I'm kind of doing like a second derivative but with respect to y. And so this is going to create a mixed partial of f, z, then y. If I subtract from that, I'm going to have here an f, y, z. Well, now I can go ahead and move to my middle term. I can see again this is going to have a negative on it, so let's see what we come up with here. I'm going to have an fzx minus, and I'm going to have a fx and then partialed with respect to z. All right, and then for my final component here, I'm going to have fyx and then fxy. So fyx minus fxy. Now, since I am able to calculate this, I could potentially stop here in that I kind of have what the curl is, but I'm going to attempt to simplify what's listed here using some important facts about what we know if it's the case that we have a function that has continuous second-order partial derivatives. Now, what I might actually recall is something from way back in Chapter 3. So we can say this. In Chapter 3, we established that if f has continuous second-order partials, if that's the case, then if they have continuous second-order partials, then these mixed partials must be equal. You may possibly recall this, although it's been a long time. Well, I think we had this somewhere at the end of maybe 3.3, where we defined partial derivatives, is that, again, if I have these continuous second-order partials, then I know that actually these two mixed partials here are actually going to end up being equal. And of course, what that means is that I can actually simplify the curl of the gradient of f. I can simplify that down to just the vector 0, comma, well, let's see, these two things are going to be equal, so 0, and these two things would have to be equal, 0. This is actually just the 0 vector. So the curl for the gradient of a function that has continuous second order partials is automatically going to be 0. Notice this is completely independent then of what the function actually is, as long as it has this special property that's true. So this particular example leads us to the theorem that's on the next page that says, if I have a vector field, not a function, but a vector field, and I know that that vector field is conservative, keep in mind that when we say that a vector field is going to be conservative, that means that there is some function out there whose gradient is going to be equal to that f. So that means that there is a function whose gradient creates the f, just like we had up here. There was a function and we did the gradient of it down here. So if I have then that p, q, and r have continuous first order partials, notice that would be the second derivatives that would come out of here, right? First derivative would take me to f with the p, the q, and the r, but the second derivative would be the derivatives of p, q, and r. So if those have continuous first order partials, then f has continuous second order partials. Well, then it has to be the case, like we saw above, that the curl of that vector field is 0. So this is a really powerful idea, but again, it's just telling me that if I have a conservative vector field, I know that vector field came from somewhere. I know there's an f that generates that capital F, and so I can easily apply the argument from up above. So we can use this for a variety of different purposes, but one of the things that we can use it for is to actually be able to help show when a vector field is not conservative. Remember that previously, in order to show that a vector field was conservative, we oftentimes would just try to find the function f, where when I took the gradient of it, it would generate my vector field. However, that was sometimes a bit tricky. We developed some extra theorems and properties in 5.3 to help with this. However, we can see that this new fact gives us something really powerful to work with. If a vector field is conservative and meets the conditions, then it has to be the case that the curl is 0. There's never a conservative vector field that has a curl with anything else than besides 0. So we can go ahead then and actually note the following. So quickly, let's just double check that if this right here is my p, this right here is my q, and this over here is my r, well, these all have continuous first order partials. Well, yeah, those are all polynomial pieces, so we can start by saying that we note the components of f have continuous first order partials. Those are good. Got continuous first order partials. Also, we can go ahead and attempt to compute the curl of f. All right, well, let's see what we come up with here. If I want to try to compute the curl of f, again, I set up everything like I normally do. So partial with respect to x, partial with respect to y, partial with respect to z, and then I got to do my xz, xyz, and a negative y squared. Fill in my I, j, and k, and then go ahead and start my computation. Well, let's see what we come up with here. We see that if I start by calculating my first component, I'm going to have partial with respect to y of my negative y squared. So that's negative 2y, and then minus my partial with respect to z. So that would be xy. I can then go ahead and calculate partial with respect to x of negative y squared, so that's going to be 0. And then partial with respect to z of xz, so that's going to be x. For my last piece here, I'm going to have partial with respect to x of this, which is yz. And then I'm going to have partial with respect to y, which is going to be minus 0. Now, if I take a look at what I ultimately ended up with here, I can definitely see very, very quickly that this is not 0. And so since the curl of f did not come out to be equal to 0, but I had continuous first-order partials, then f is not conservative. There's no way it could be conservative, because again, every conservative vector field that has continuous first-order partials is going to end up with a curl of f. So this theorem provides us with a nice way to kind of double check to see whether certain vector fields are conservative.